In this video, I want to talk a little bit about the binomial distribution and how that interacts with R. What I've done to give you a little bit of a background, of course, I'm assuming that you already are familiar with the binomial distribution and what it does. But what I have here is I have a graph that I created in Desmos, which is the binomial distribution for n equals 10. I just picked a concrete value of n so that the programming was a little easier. Well, the inputting was a little easier, and then we can kind of play around with it from there. So you can change the value of P, and I can post this so that you can kind of play around with it and see how the different distribution changes for different P values. But the idea with this distribution, and let's go to the worksheet that we have, but the idea with this distribution is that we want to count. We have some idea of success and failure. And again, remember that success doesn't necessarily mean good. It just means that the thing that we're trying to count happens. And failure doesn't necessarily mean bad. It just means the thing that we're trying to count doesn't happen. So again, they just use the word success and failure to say either it happens or it doesn't happen. But anyway, so let's say that we have n trials. So we want to do this thing n times, and then we have a probability of P of it happening. And then the binomial distribution will tell us what's the probability that we have, say, X successes out of n trials with probability P. And if we wanted to, we could compute that formula. That's what this formula is here. That's the binomial probability formula. And again, n choose X is the binomial coefficient. Those are the values that you're used to seeing in Pascal's triangle. So those are, again, called binomial coefficients. So I have a graph that kind of mimics what this distribution is going to look like, and it has those values computed. And when P is 0.5, that means that the probability of a success and failure is completely equal, and therefore you get symmetry in the distribution. And so that's why you notice that the probability of it happening one time is the same as the probability of it happening 9 times. So the probabilities you interpret not as heights, but as areas. In this case, the height is the area because these are rectangles of width 1, but I want you to get used to the idea of interpreting probability in regards to area of some region, in this case, rectangles. And so we can count, what's the probability that some event happens 0 or 1 or 2 times, and you can add up those areas that will give you that probability. And as P changes, this distribution is going to also shift a little bit. So it's going to look a little bit differently. And so, if P is 0.8, then it's very unlikely when you do something 10 times and there's an 80% chance of it happening, it's very unlikely that it'll happen 0, 1, or 2, or even 3 times. And we can quantify that. We can come up with what are the exact numbers here. But this is, again, just something to kind of get used to playing around with. Okay, so as P is small, this gets concentrated around the left. And when P is large, by large, I mean close to 1, the distribution gets skewed to the right. So anyways, this is what the distribution looks like. Now, let's just pick a probability. Let's say 0.59. Okay, that's maybe a little bit too symmetric. Let me actually do it. Let's do 0.72. If we wanted to calculate what's the probability of having exactly 4 successes out of 10 trials, it looks like the probability is about 0.04. Notice all these probabilities add up to 1, which is why all the probabilities are scaled the way that they are. So let's say I wanted to compute what is this probability of having 4 successes, exactly 4 successes out of 10 trials, where the probability of a success is 0.72. And so with that, we could use R. And the way that we're going to use R, let's get rid of our examples here for a second. But the way we're going to use R is we would use the D binomial function. And so we want to have 4 successes out of 10 trials and a probability of 0.72. And we're hoping that the answer is somewhere around 0.04. That's graphically what it looked like. And it's about 0.03, 0.027. Okay, so that's the D binomial button. So if we look back, yeah, and actually if we go to Desmos and look at what the height is, I'm just bad at estimating heights. This is 0.0272. That's the height of that. And then if we go back to R, we get 0.0272. Okay, so those, again, those agree up to 4 decimal places. That's basically what the D binomial function does, is it tells you what's the probability of having exactly 4 successes of 10 trials with a probability of 0.72, right? And then you of course can change the numbers to fit whatever example you'd like to do. If I wanted to compute the probability of, say, 0, 1, 2, 3, or 4 trials, that's also going to be a very small number, because 0, 1, and 2, you can quantify how big those are. But if we add up these areas, what we would want to use then is the P binomial function. And the P binomial function tells you what's the probability of having 4 or fewer trials. So in other words, what's the probability of having exactly 4 or exactly 3 or exactly 2 or exactly 1 or exactly 0 successes? And that'll be just a little bit larger than this 0.027, 0.034. And again, that little bit larger really reflects the fact that those rectangles that we were looking at in the graph before were really small. Okay, so these heights are really small. So 0.0009, it's not adding much to the total, and so on. Okay, and so that's what these values are going to do. And if I wanted to find, say, the probability of having 5, 6, or 7 successes, there's 2 ways that we could do that. So if I want to find the probability of having 5, 6, or 7 successes, I could find the probability of having 7 or fewer successes minus the probability of having 4 or fewer successes. And then what I would be left with is the probability of having 5, 6, or 7 successes. Okay, so if we add those up, that's how we could do that. The other way that you could do this is you could add the values. You could sum the values of the D binomial distribution, where we go from 5 to 7. That's another way to do the same calculation. So this D binomial, when you give it a range, what it's going to do is it's going to spit out a few values. So you could get those values. In fact, if you wanted to figure out what are the numbers in the entire distribution, when the probability of P is 0.72, you could just type D binom 0 to 10. You have 10 trials, and then our probability P is 0.72. And then this will give you the 11 values. There are 11 values because you have 11 different numbers of successes that you can have. You can have 0 successes, and then 1, 2, 3, 4, all the way up to 10 successes. So there's 11 different outcomes. And this gives you these values to whatever accuracy you'd like. So if you want to find the probability of, say, getting exactly, what were we looking at before? Exactly 4 successes, that was this one. So that was 2.719 times 10 to the minus 2. So that means 0.027195553. And so that E minus 0.02 is just a way of saying times 10 to the minus 2. And you'd have to do the same for all of these as well. Okay. And so that's the D binomial and the P binomial functions. If I wanted to find the probability of having, say, 8 or more successes, what you could do is you could just do 1 minus the probability of having 7 or fewer successes. So if I wanted to find, let me say it again, if I wanted to find the probability of having 8 or more successes, that's 8, 9, or 10, I could just find the probability of having the complement of 8 or more, 7 or less, 7 or fewer successes. And I would take 1 minus that. And so that would be the probability of having 8 or more successes. And again, you could do this either way you wanted to. You could do the 1 minus the P binomial, or you could add up the D binomial values. So this would be 8 to 10 with 10 trials and probability 0.72. And so that's basically how Chapter 5 interacts with R. The only other things that I really have to say, and let me just kind of point out, there's also this worksheet that I have. It's not a worksheet, it's a Google document that has the stuff for the binomial distribution. So this is the D binomial and P binomial. Q binomial and R binomial don't come up a lot. I kind of just included those for completeness, but you can ignore those for now. We really only need the D binomial and P binomial for our course for right now. Q binomial gives you something, and we'll talk about what the Q functions do. I think it'll make a little bit more sense in chapter 6 when we talk about the normal distribution. R binomial, R is just a random number generator. So this is just going to say, if you wanted to come up with, a certain number of random numbers from this distribution, it could tell you, it could do something like that. So anyways, we'll leave those alone for now. The only other things that I want to say about chapter 5 that are going to be relevant for us is that if we look at the chapter 5 formulas, the other things that get used are the standard deviation of the standard deviation of a discrete random variable and the mean of a discrete random variable. So the expected value and the standard deviation of discrete random variables. When you have a binomial distribution, the formulas are very nice and very easy. We talked a little bit about that in the chapter 5 material. But in general, when you talk about standard deviation of a distribution or the mean, those are also formulas that come up. And so I also have those on the R commands. So that's these discrete random variables part. So if you have to find the expected value of a distribution or the standard deviation of a distribution, that's how you do those. Okay, so that's what those are. So that's chapter 5 in R.